Capacitors are devices that are widely used in electric circuits. They are used to store electric charge and energy. Here are two examples of capacitors. A capacitor consists of two conductors with equal and opposite charges. The conductors in a capacitor are called plates, regardless of their shape. The potential difference V between the two capacitors is proportional to the charge Q on them. This is reasonable, since doubling the charge doubles the electric field, and therefore the voltage difference. The constant of proportionality between the voltage and the charge is called the capacitance C. The capacitance is a measure of the capacitor's ability to store charge. Rearrange the equation as shown. The unit of capacitance is the farad, which is equal to 1 coulomb per volt. The capacitance of typical capacitors is typically much less than 1 farad. Units more commonly used are the microfarad, equal to 10 to the minus 6 farads, and the picofarad, which is equal to 10 to the minus 12 farads. The two objects shown are charged until the voltage difference is 1200 volts. The objects have equal and opposite charges of magnitude 8 times 10 to the minus 6 coulombs. What is the capacitance of this system? Correct. Here is the solution. A parallel plate capacitor consists of two flat plates of area A separated by a distance d. When each plate is given a charge of magnitude Q, an electric field E will be present between the plates. If the separation is small enough, the field strength and direction will be nearly constant. Because the electric field between the plates is constant, the voltage difference between the plates is the electric field magnitude times the separation d. The capacitance of a parallel plate capacitor is proportional to the plate area divided by their separation. As this equation indicates, the larger the area of the plates, the larger the capacitance, and the closer together the plates are, the greater the capacitance. If the plates get too close to each other, however, the charge could jump from one plate to the other. A very large parallel plate capacitor has square plates that are 10 centimeters by 10 centimeters in area and are separated by 1.0 millimeter. What is the capacitance of this capacitor?
Try again. Try again.
Correct. Check the solution. To charge a capacitor, it is necessary to connect it to an external voltage source, such as a battery. The battery maintains a steady voltage V across the capacitor. If the plates of the capacitor are moved closer together, the capacitance will increase. Because the battery maintains a constant voltage across the capacitor, the charge on the plates will increase proportionally. If the battery is disconnected from the capacitor, the consequence of moving the plates will be different. In this case, the charge on the capacitor plates remains constant as the plates are moved, because the plates are disconnected from the battery. Since the charge remains constant, when the capacitance changes, the voltage must also change. A 10 picofarad parallel plate capacitor is charged by connecting it to a 9-volt battery, after which the battery is disconnected. Next, the plate separation is doubled. What is the final voltage across the capacitor?
Try again. Try again.
Correct. Review the solution. Another kind of capacitor is the cylindrical capacitor. In this kind of capacitor, a cylindrical conductor is nested within a larger, hollow cylindrical conductor. Consider a cross-section of this capacitor. The inner and outer cylindrical conductors comprise the plates of this capacitor. If there is a charge Q on the capacitor, electric field lines extend radially between the plates because of the symmetry of the device. The symmetry of the conductor also results in an electric field magnitude that is a function of the radius only. we assume that the plates are long enough for the symmetry argument to apply. Apply Gauss's law to the problem by creating a Gaussian surface between the plates. This surface is cylindrical with radius r. The caps of the cylindrical Gaussian surface are perpendicular to the electric field and thus do not contribute to the integral. The electric field is perpendicular to the curved part of the surface and constant in magnitude. Thus, the result from Gauss's law reduces to the equation shown. The voltage difference between the capacitor plates can be obtained by integrating the electric field between the capacitor plates. Solve for the capacitance. As with the parallel plate capacitor, the capacitance increases when the plates are moved closer together. Calculating the capacitance of a spherical capacitor entails following a similar procedure. The electric field lines are straight and directed radially. Apply Gauss's law using a spherical surface of radius r between the two plates. The electric field is constant in magnitude at the spherical Gaussian surface and perpendicular to it. Next, calculate the voltage difference and solve for the capacitance. As before, the capacitance increases when the plates are closer together. The plates of a spherical capacitor have radii of 70.0 centimeters and 71.0 centimeters. What is the capacitance of the capacitor? Correct. Review the solution. Capacitors store energy as well as charge. When a capacitor is discharged, the energy is released. Usually, the energy release is more controlled than in this case. We can calculate the amount of energy stored on the capacitor. Consider a capacitor that is charged to a voltage V. The energy dU needed to add an additional increment of charge dQ to the capacitor is V times dQ. The voltage between capacitor plates is equal to the charge divided by the capacitance. We substitute to obtain the equation shown. Integrate this from a charge of 0 to a final charge capital Q on the capacitor. Evaluate the integral. The energy stored on a parallel plate capacitor is the charge squared divided by twice the capacitance. This result can also be represented in terms of the voltage on the capacitor by applying the definition of capacitance. A capacitor is charged to 9 volts and contains 10 joules of energy. What is the capacitance of the capacitor?
Try again.
Correct. Here is the solution. The energy stored in a capacitor is contained in the electric field. The definition of energy density is the energy per unit volume. We can calculate the energy density associated with the electric field for the case of a parallel plate capacitor. The volume between the plates of a parallel plate capacitor is the area A times the plate separation D. We previously introduced expressions relating the electric field and the energy in a capacitor to the voltage between the plates. We also have the equation for the capacitance of a parallel plate capacitor. Now we make substitutions in the energy density expression as shown, and find that the energy density is proportional to the square of the electric field. While we have derived this equation for the special case of a parallel plate capacitor, it is true in general.